Hi and welcome to this video where we're going to look at financial maths exam questions. Example 7.1, converting interest rates. So just a little bit of background about this. We are going to see APR, which stands for annual percentage rate, and that's an interest rate for when we're borrowing, or an AER, which stands for annual effective rate, which is the interest rate when we're saving. And both of these are a rate which you would get if the interest rate was applied annually. However, just from a pure logistical point of view, that is not feasible in the real world. So it's more likely that the rate of interest will be applied a lot more frequently. In our questions, we've only ever really seen it go to monthly, but we have seen on mock papers where it goes to weekly. Same logic applies. So if they did give you a question where it was weekly, you will be able to work with it in exactly the same way. It's actually a legal requirement for any kind of loans to display an APR so that you can easily compare across money lenders, banks, building societies, credit unions, etc. So it's a really important thing, not just for your exam, but for the future to understand. So let's look at the question. Donna is arranging a loan and is examining two different repayment options. Bank A will charge him a monthly interest. Let's get some highlighting going. Of 0.35%. Find correct to three significant figures and the annual percentage rate that is equivalent to that monthly. So what we have is we basically say, well, if we invested, and I'm using this formula over here, the F is equal to P bracket 1 plus I to the power of T. I'm only focusing on the 1 plus I to the power of T because we would have invested the same. So 1 plus 0.35% is actually 0.0035, and if we compound that monthly, that will be the same as 1 plus an interest rate basically compounded yearly, and that I will then be my APR. So working that through, we can get I is equal to 1.0035 to the power of 12 minus 1. I don't like working with decimals, so if I can avoid it, I will. And we get 0.042818. And that gives us, as a percentage, correct three significant figures, 4.28%. Significant figures, non-zero numbers. So Bank B will charge him a rate that is equivalent to an APR of 4.5%. Find correct three significant figures, the monthly interest rate that is equivalent to an APR of 4.5%. So in this case, we would say 1 plus some rate that we don't know, compounded monthly, will be the same as 1 plus 0.045 compounded for 1 year. So working that through, we get 1 plus or to the power of 12 is equal to 1.045. To work backwards from a power of 12, it is the 12th root. So it's like a square root, but it has a 12 here. And I will, again, try and avoid writing decimals for as long as I can. And that gives us 0.0036748, which is, in percentage terms, they said three significant figures, 367%. So example 7.2, savings. So Neva saved to buy a car. She has saved an equal amount at the beginning of each month into an account that had earned an AER, so that's the annual effective rate, of 4%. So show that the rate of interest compounded monthly, which is equivalent to the AER of 4%, is 0.327%. So just like the last one, we're going to have 1 plus some monthly rate compounded monthly should be the same as 1 plus 0.04 compounded over 1 year. Excuse me. So 1 plus or to the power of 12 is equal to 1.04. Working backwards, that gives me the 12th root of 1.04. So or is equal to the 12th root of 1.04 minus 1. So or will be equal to, in that case, 0.003274, and 3 decimal places, that's after we turn it to percentage, is going to be 327%, and that is exactly what we were asked. QED. The second part of this question, Neve has 15,000 in her account at the end of 36 months. How much has she saved each month correct to the nearest euro? So I think it's really, really important that you draw this out in a way that helps you make sense of the question. So Neve has 15,000 here. So we know the amount she has at the end. So there's her 15,000 here at the end. That's at the end of 36 months. So what she did was she invested a certain amount each month. So let's call that amount P. This first P, which she invested, was going to be invested for 36 months. Then the next time she puts in that P, she's going to only have that invested for 35 months because it's the following month. And then the next month she puts in a certain amount, and it's 1 plus or to the power of 34 plus and then plus P times 1 plus or to the power of 1. And when they're all added together, it should give you that 15,000. So it's really important that I would always start with, where is that lump sum? Is it beforehand? So are we talking about bringing it backwards? Or is it at the end? Are we talking about bringing it forward? And forward, I'm talking about my future value. Bringing it back, I'm talking about my present value. So what we have here is a little, now I know I haven't put in any numbers for or I don't know P, that's what we're looking for. But effectively what we end up with, and what you will always end up with when we're talking financial maths, is a geometric sequence. So basically each time you've effectively divided by a 1 plus or. Okay, 1 plus or, and so on. 1 plus or. So what we're going to use is we're going to use the idea of a sum of a geometric sequence. So the sum of a geometric sequence needs a few things. The first thing it needs is A, which is the first term, which is P bracket 1 plus or to the power of 36. Now we already know what that is because we worked out or in the previous question, the previous part, part I. So we have 1 plus, now be careful, this should be in decimal form. So it's 0.00327, and that is to the power of 36. P bracket 1.00327 to the power of 36. That's my first term. Second thing it needs is or, which is the common ratio, which is 1 over 1 plus or, which is going to be 1 over, we just worked that out, 1.00327. You can do it to the power of minus 1 if you want, but it's absolutely fine like this. We're going to sub it into our formula. So the formula we're going to have is S36, so it's Sn, is equal to A, which is P 1.00327 to the power of 36, times 1 minus or 1 over 1.00327 to the power of n, which is 36, all over 1 minus or 1 minus 1 over 1.00327, and that whole thing should work out to be 15,000 when you add all those together. Now, students often struggle a little bit with questions like this because there's a lot going on with it. However, where our P is, it's basically multiplying by the top line. So we can pull out our P, and it's going to be P multiplied by that red bracket. So that red bracket can actually go straight into your calculator. So when you work that piece out, you'll be able to get a number for it, and it completely simplifies our sum. You don't have to work that way. You can work by breaking down each individual piece, but because that P is multiplied by everything, we can effectively pull it out to the front. So when we put that into the calculator, we should get 38.26326387. So P times that should equal 15,000. So in order to work out P, we're going to divide by that 38.26326387. And same here, 38.26326387. And that will give us, correct to 2 decimal places, 39202. And they've asked it correct to the nearest euro, which is 392 euro. So sometimes students really find those quite confusing because there's so much going on, there's so many fractions. But if we're ever using the sum formula, so the sum of a series, sum of a geometric series, so formula, and you're looking for that P, so that amount that you're putting in each time, remember that that can be pulled out and ignored. That little trick can be used in so many different questions, and it simplifies the question so much. These are the bits that students tend to get wrong, and understanding what you can put into the calculator when we're talking in algebraic terms, so when there's a letter there, it will make all the difference. Example 7.3, pension payouts. So Acme Confectionery has an employee pension plan. For an employee who qualifies for the full pension, Acme Confectionery will pay a sum of 20,000 on the day of retirement. So there's quite a lot of reading going on here, so I'm going to highlight as we go. And it's on the day of retirement. That's important. So there's no delay. It happens straight away. It will then pay a sum on the same date each subsequent year. So each year for 25 years. There's 25 payouts. Each year the employee is paid a sum that is 1% more than the amount paid the previous year. What sum of money must the company set aside on the day of retirement in order to fund this pension? Assume an AER of 2.4%. So I will always suggest drawing that out. We're looking for this thing here. So here is the pension fund. They want to have a fund sitting here. Okay. And from that fund, they're going to start paying out. And the first payout is going to be 20,000. Now, it is straight away, so there's no interest. There's no need to bring that back to anything. The second payout in a year's time is actually 1% more. So if we add 1% on to 20,000, we could figure that out. And that would be 20,200. However, I'm going to be a little bit clever here and keep that 20,000 and basically increase it by multiplying it by 1.1. Okay, sorry, 1.01. So only 1%, not 10%, unfortunately. 1.01. And then, because that happened a year later, we're going to have to find the present value of that. They don't actually need that full amount of money because they would have got a little bit of interest. So what we do to work out the present value, so to bring it back, is we divide it by 1 plus the interest rate. So 1 plus 0.024 all to the power of 1. Okay. So that's in 1 year time. So if it helps, we can call this year 0. So that's the start. That's year 1. So at the end of year 1, and so on, year 2. So the next one, what we're going to end up with is still got that 20,000. I'm keeping that. I know we could work out the amount, but that's not going to be hugely helpful as we get further into the question. So actually, if I square that 1.01, because effectively what happened is I have the previous year, so 20,000 by 1.01, and multiply by 1.01 again. Same thing happens here, so I'm going to just clean it up a bit. 24 to the power of 2, and so on. And that's going to go on until effectively the end of 25 years. So it's going to be 20,000 1.01 to the power of 25 all over 1.024 to the power of 25, and that is year 25. So it's a little bit more complex. That 1.01 just made it a little bit more complex. So here, excuse me, what we have is a geometric sequence, and to get from the first to the second, I'm multiplying by 1.01 over 1.024, and that's going to happen each time. Multiply by 1.01, 1.024, and so on. So that 1.01 over 1.024, that is our OR. So remember, there's two things we need. We need A, which is the start, so that's 20,000, and we need OR, the common ratio, which is 1.01 all over 1.024. This time we're going to go straight into the formula. Now, we just need to be careful, because when we're dealing with the formula, our n is actually going to be 26. Because even though we have 25 years, we have that the starting year, that year 0, because it's 20,000 on the day of retirement. And then a sum is paid each subsequent year for the next 25 years. So there's actually 26 pieces. And if you look at our little diagram here, you can see actually, yeah, if it starts at year 0 and goes to year 25, that will be 26. So we need to be able to sub into our formula. The formula is Sn, which in our case is 26, is equal to A, which is 20,000, times 1 minus OR to the power of n, 1.024 to the power of 26, all over 1 minus OR, 1.024. And you can put that straight into the calculator, just be really, really careful. And that gives us our total of 440.40. It is money, so we're going to do 2 decimal places. So example 7.4, amortization of a loan. Donna borrowed 80,000. Let me just highlight important pieces. 80,000 at a monthly interest, so that's monthly interest rate of 0.35% for the fixed term of a loan from Bank A. So this was actually a follow-on from our example in 7.1, but we're just looking at them separately. The first repayment is due 1 month after the loan is issued. That's important. And calculate correct to the nearest euro the amount of each monthly repayment. Now, if you're trying to figure out the equal amount to pay back a loan, we have a formula which is in the log tables, and it is this formula here. It's the amortization of mortgages and loans. So it's where there is equal repayments at equal intervals, and the only other thing you need to remember, you can only use it if the repayment is due 1 month or 1 year or 1 period after the loan is issued. So what we effectively have is our formula. A is the annual repayment, or in our case the monthly, because everything that they say is annual, so their I we're going to put in as monthly. So to figure out our A, we have P, which is the principal, that's 80,000, and we have I, which is 0, and these must be in decimal, so it's 0.0035. So remember, if you need to divide your percentage by 1,000, it's very easy to just stick it in as is, because there's already a decimal point in it. So just be very careful with that. So to the power of t, so we're talking about a 10-year loan. So actually, apologies, so 10-year loan, I never highlighted that. So 10 years, and when we talk about 10 years, monthly, we're doing 10 by 12, which is 120 months. So this is 120 all over 1.0035 to the power of 120 minus 1. And that can all go into the calculator. And when it does, we get 817.59. And they've asked us correct the nearest euro, so watch out for that, which is 818 euro. Now, you don't have to use that amortization formula. The amortization formula actually comes from the sum of a geometric sequence. So you can set these up as a sum of a geometric sequence. My question is, why would you when you have that formula there? To get a better understanding of the formula,